Hey guys, Mr. B here, and in this video we're going to be going through chapter 14.4 on simple machines. So, yeah, let's start off. We're just talking about what is a simple machine. So, we already talked about machines in the previous chapter section, and that of course is any object that essentially can make work easier for us to do. And a machine is something that can do one of three things. It can either increase our force, or change the amount of force needed. It can increase or decrease the distance over which our force acts, or it can change the direction of the force that we apply. And so there are 6 types of what we call simple machines, and simple machines are, I don't want to say smaller, but more simplified versions of machines. And then there's certainly complex machines, which are things that essentially involve all of these simple machines or multiple of them to get built, like a car, for example. Okay, so the 6 types of simple machines we have are the lever, the wheel and axle, the inclined plane or the ramp, the wedge, the screw, and the pulley. So we're going to talk about each one of these and how each one works, and also in terms of what they do. So first one we have is the lever. So a lever is a rigid bar, so something that is, not flexible, and it's free to move around a fixed point that we call a fulcrum. Okay, so this is called a lever, where again it's a fixed bar and it rotates around a fixed point called a fulcrum. Okay, there are 3 categories of levers, and the categories are based on where the input force is, where the output force is, and where the fulcrum is. So this is an example of a teeter-totter, which is a lever. Okay, this would be a first class lever, and we'll look at the other classes here in a second. But we see that the fulcrum is in the middle. We have our input, or our effort is what we call it. Okay, this is the input arm, or the location where we have to push down or put the force. We have our output arm, or our resistance, with the load, which is the thing that we're trying to move or lift. Okay, the output force is, again, the distance that the length of the lever is from the fulcrum to the thing you're moving. Now, levers, in terms of their mechanical advantage and how they work. So remember, mechanical advantage, and this is from the last chapter section, mechanical advantage is how much a machine essentially helps you, okay, or makes you stronger. So to calculate the ideal mechanical advantage of a lever, we need to take the input distance or input arm and divide that by the length of the output distance or the output arm. So essentially think of a teeter-totter like this, where the fulcrum is right in the middle. If we take the input distance, and let's say that this is, 5 feet, and divide that by the output arm, which is also 5 feet, this would give us a mechanical advantage of 1, meaning this would not make us any stronger or weaker. The amount of force needed to lift this object would be the same amount of force that you need to push down on this side. However, if we start moving this fulcrum either closer towards where we're pushing or closer towards where the load is, then we start to get a mechanical advantage greater than 1 or less than 1. Okay? So here are the 3 different classes of levers. And again, we'll notice that they are classified based on where the fulcrum is, where the input or the effort is, and where the output or the resistance is. So in a first class lever, it is a basic teeter-totter. You have your fulcrum in the middle, and you have the input and the output on opposite sides of the fulcrum. So again, a teeter-totter, there's a picture here of a crowbar lifting up like a rock. Scissors, okay, the pivot point on a pair of scissors, and let's actually zoom in here so we can see better. Okay, so the pivot point on a pair of scissors is right in the middle. The effort is where you're pushing, and then the load is what the scissors is cutting. If you're using like a screwdriver to open up a paint can, then where you're pushing is the input. The lip of the can that the screwdriver is on is the fulcrum. That's where it pivots from. And the tiny little portion that's underneath the lid of the paint can is the output or the resistance. Okay, that's a first class lever. Second class lever, we now take the fulcrum and put it on the end. And the resistance, or the thing we're lifting, is now in the middle. So we still have our input, or where we're putting an effort, on the end, but the fulcrum, instead of being in the middle, is now on the other end, and the thing we're lifting is in the middle. So a primary example of a second class lever is going to be a wheelbarrow, where we are lifting from the end. The heavy thing that we're lifting is in the middle, and where we're pivoting from is the wheel, okay, which is located, of course, on the other end. Another example of this would be a nutcracker. So you have, of course, the fulcrum or the pivot point at one end, where you grab and squeeze, okay, is the input on the other end, and then the thing you're trying to break is the nut that's in the middle, and that is the resistance or the load. Last one we can think of is a car door, or basically any door actually is a second class lever. The fulcrum is the hinge, okay, the door hinge where it pivots from. The heavy part is the actual door itself, which has all the weight. And then the effort, or the part where we are pushing or pulling, is the very end, right? When you open a door, you typically grab it by the very end, which is the handle or the doorknob, and the door hinge is over here, the door is here, and then we grab it on the other end, right? That's a second class lever. As for a third class lever, now we take the input and we put it in the middle. So instead of being the resistance in the middle, now we're grabbing it in the middle and moving it from there. The fulcrum is on one end and the resistance or the heavy thing is on the other. So primary example of this is a broom or any kind of like a golf club or a hockey stick, where we are grabbing in the middle. Okay, we grab in the middle and we move it like this. The fulcrum, the pivot point, is the top. Okay, that's where it pivots from. So when you're moving a broom like this part here up here is where it's pivoting from. We're grabbing in the middle, and the heavy part is the bottom of the broom that's sweeping along the floor that has the weight and all the brush and bristles on it. Tweezers is another example of, tweezers is another example of a third class lever, right? If you grab a pair of tweezers, the pivot point is at the very end where the two pieces of metal are fused together. You grab tweezers in the middle, but then on the very end here, this is the part that's grabbing something. So this is the resistance. The input is where you're grabbing in the middle, and then the fulcrum is the end. Salad tongs, or if you ever grilled anything with tongs before, same thing. This is a third class lever. A fishing rod is a third class lever. If you hold a fishing rod like this, it pivots from the very bottom, right? So when you go like this with a fishing rod, the very bottom is the pivot point. You're grabbing here on the handle in the middle. Again, it pivots from here. You grab here, and then the heavy part is the lure or whatever's on the end of the fishing rod up here, okay? So that is also a third class lever. So anyway, there's lots of other examples of different class levers, but those are just a few. So let's move on to talk about the next simple machine, which is a wheel and axle. So a wheel and axle is a simple machine that basically consists of two discs or two cylinders, each with a different radius or a different size. Okay, usually on a wheel and axle, the outer disc is the wheel and the inner cylinder is the axle, right? So you have an axle like this with then a wheel attached to it, and they rotate together. So as you rotate the axle, the wheel also rotates along with it, okay? To calculate our ideal mechanical advantage for a wheel and axle, we're going to divide the radius where the input force is exerted. So we're going to basically divide the radius of the wheel by the radius of the axle, okay? So you have the two different sizes, and you're going to divide those two. And again, there's a picture here that shows this. So to find our mechanical advantage of our wheel, or our wheel and axle, we take the radius of the wheel, so from the middle all the way to the edge, that's the radius, and divide that by the radius of the axle, which is usually a lot smaller, okay? Now, the larger wheel that you have, okay, the larger the wheel compared to the size of the axle, you will get a greater mechanical advantage. So you're going to get more out. However, it's more difficult to rotate the axle if the wheel is very large compared to it. So imagine that you had a giant wheel this big on a pencil, right? That's only this wide. It'd be very difficult to rotate that because of how forces and work and machines work, okay? So the mechanical advantage for a wheel and axle is easy to calculate, but it can get very interesting. All right, next up we have an inclined plane, or the ramp. So this, of course, is a slanted surface and essentially moves an object to a different elevation. So you use a ramp to lift heavy objects, right? Rather than pick them up and lift them yourself, you push them up the ramp. Basically what a ramp does is it increases the input distance. So the input distance is the distance you have to push the object up the ramp, and the output distance is the height that the ramp is lifting the object for you, okay? So basically this is, the longer the ramp, the more mechanical advantage you're going to get. So to find the mechanical advantage for a ramp, you're going to take the distance along the inclined plane and divide that by the change in height. Okay, so we're going to take input distance divided by output distance. That will tell you the mechanical advantage. And basically, the longer your ramp is, the more mechanical advantage you'll get. However, the downside is the longer your ramp is, the further you have to push that box up the ramp to get to the top. So, all right, three more. So the next one we have are wedges and screws. A wedge is a V-shaped object whose sides are two inclined planes that are essentially sloped towards each other. So it's something like this. An axe is an inclined plane. And basically for wedges, a thin wedge of a given length, okay, so thin means it's not very wide. So right, thin was like this. So thin wedge of a given length has a greater mechanical advantage than a thick wedge. So if we're going to use a wedge, we want the wedge to be thin like this. We don't want it to be thick like this, okay? We don't need to worry too much about mechanical advantage for wedges. We won't really calculate those. Screws. A screw is basically an inclined plane that's wrapped around a cylinder. So we can look at it, this picture here, basically imagine that you have a cylinder and you take an inclined plane and you wrap it around the cylinder. So screws with threads that are closer together have a greater mechanical advantage than screws with threads that are longer apart from each other. Okay, so if you see a screw with lots of threads that are all right next to each other, that's going to have a really good mechanical advantage. The downside, though, is that you're going to have to twist that screw a lot of times to get it to go all the way in because you have to wrap all the way around the whole thing. All right, and the last thing we have here is a pulley. So a pulley is a simple machine that consists of a rope that fits into a groove in a wheel. Pulleys produce an output force that is different in both size, or it can be in size, direction, or both. Okay, so basically what this is saying is a pulley can make it so that you have to use less force. It can make it so that you have to pull down instead of pulling up, or it can do both. And so there are some images we'll take a look at here in a second. But the ideal mechanical advantage of a pulley or a pulley system is going to be equal to the number of rope sections supporting the object that you are lifting. Okay, so here is 4 pulleys, and this is going to show you exactly what we're talking about. Okay, so we're going to zoom in on each one here. So this is what's known as a fixed pulley. And in a fixed pulley, in a fixed pulley, you have a pulley that is essentially fixed in place. So it's attached to the ceiling, can't go anywhere. You have your heavy object down here at the bottom. So if we count how many ropes are pulling up on this heavy object, we just have this one. Okay, this one rope is pulling up. This part of the rope you are pulling downwards, okay, but this part of the rope is pulling up. So the mechanical advantage of this pulley system is going to be 1. It's 1 to 1. What basically means is this pulley system would not make it any easier for you to lift this object. If it weighs 100 newtons, you're going to have to pull the rope with 100 newtons of force because it's not helping you. Okay, all it's doing is it's changing direction. You're pulling down, it lifts up, but it doesn't make it easier. This pulley system is a movable pulley. So we have a fixed pulley up at the top, and then we have a pulley down here at the bottom that can move. So as you pull the rope, this pulley will move upwards with the object. Now, if we look at how many ropes we have here, we have 2 ropes. We have this rope here pulling upwards and this rope here pulling upwards. Each one gives you a mechanical advantage of 1. So total, this has a mechanical advantage of 2, which means that you only need to use half the force to lift this object. So if this object is 100 newtons, you only have to pull with 50 newtons of force, right? Half of the amount of force. This third one here, this is called a block and tackle. So now we have essentially 2 fixed pulleys and a movable pulley. So we're kind of putting a lot of things together. And if we count how many rope strings we have here, we have 3 rope strings. We have 1 here, 1 in the middle, 1 on the right. Each one is going to give you a mechanical advantage of 1. So this is going to have a mechanical advantage of 3, and it will reduce the amount of force you need to use by a factor of 3. So to lift this 100 Newton object, you only need to use 33.3 newtons of force. So a lot simpler to use, okay? The last one is another block and tackle. It's just more complicated. If we count all the ropes on this, we have 1 rope, 2 ropes, 3 ropes, 4 ropes, all pulling up on this object. Therefore, it is going to reduce the amount of force you need by a factor of 4. It has a mechanical advantage of 4. So if this object is 100 newtons, you only need to pull with 25 newtons of force. So pulleys can dramatically decrease the amount of force needed to lift the object. However, here's the downside. Even though it takes less force to lift these objects, you have to pull more rope to get them to go up. So they are decreasing the amount of force you need, but they are increasing the amount of rope you have to pull, right? So with this first one, you just got to pull the rope the same amount of distance to lift the object off the ground as you would if you were just to lift it yourself. Whereas this one on the far right, you're going to probably have to pull quite a lot of bit of rope to get this object to go up. But it will be very easy to do so, okay? All right, so these, it's just going to talk about these. We just looked at all these pictures basically, but fixed pulley, the pulley is attached in a fixed location. The direction of the force is changed by a fixed pulley, but the size is not. So the mechanical advantage of a fixed pulley is always going to be 1. Okay, that's this first one. This is never going to make things easier. It just makes it so that you have to pull down instead of pulling up, but it doesn't make it easier for you to do. Movable pulley is the pulley that is attached to the object being moved rather than into a fixed location. So the pulley is going to move with the object, and they're used to reduce the input force needed to lift it. So movable pulley, again, is this bottom one. It will lift up with the object as you lift it, and it will make things easier for you by reducing the amount of force you need to use. Then lastly, we have a pulley system, which is a block and tackle. That's these last two, where you have essentially a fixed pulley and movable pulleys all put together. And these can give you very large mechanical advantages. But again, the downside is that they are also going to increase the amount of rope you have to pull to lift the object a good amount of distance. So, all right, guys, that is it for this section of notes. Hopefully that gives you a little bit more insight into simple machines and all the different types. We'll be dealing with these a little bit in class, so hopefully I can also clear up some stuff there. But anyway, if you have any questions on this, make sure that you email me and ask. Otherwise, that's it for this one, and I will see you in the next one. Bye.